question which you want expounded upon or explained further, just raise your hand. No, and, okay. So number one, which of the following elements can be used as a donor dopant? Arsenic, because it has 5 valence electrons. No? So meron ka isang electron that can be a basically donor siya, no? Kasi it has 5 valence electrons. Okay? And then a pure semiconductor, the band gap is about 1 electron volt. No? 1 electron volt to a few electron volts. No? Yung metal, what is the band gap in a metal? Wala. It's 0 because there's an overlap. There's an overlap between EC and EV sa metal. Samantalang sa insulator, the band gap is very large. It's greater than 9 electron volts. So yung sagot sa number 2 is letter C. No? And then this energy frees an extra electron from the donor atom into the conduction band. No? So the energy of the donor atom is E sub D. The conduction band is E sub C. So syempre, to free it, what you need is E sub C minus E sub D. Okay? And then which of the following statements is true for a p-type semiconductor? P-type semiconductor means your acceptor concentration is very much greater than your donor concentration. So Na is very much greater than Nd. However, for it to be a p-type semiconductor, the difference between Na and Nd should be much greater than your intrinsic concentration. Otherwise, baliwala lang yung doping mo. So that's why it's letter D. And then the Fermi level of an N-type semiconductor, okay? So yung Fermi level kapag intrinsic semiconductor is in the middle of EC and EV. Kapag N-type, umaakyat siya. Kapag P-type, bumababa siya. Okay, so if it's N-type, it will be greater than the intrinsic Fermi level E sub I. Okay. So what happens to the Fermi level of a p-type semiconductor when the temperature goes up? I think this was one of the quiz problems. So dapat alam nyo yung sagot yan, ano? This was one of the problems in the quizzes, no? Ano nangyayari sa Fermi level when the temperature goes up? Okay? Whatever happens or whatever type of semiconductor, basta tumataas yung temperature, your Fermi level will approach the intrinsic level. Okay? So if it's a p-type semiconductor, ibig sabihin yung Fermi level nasa baba, it will go up toward the intrinsic. If it's an N-type, ibig sabihin mataas yung Fermi level, it will go down toward the intrinsic. Okay. Which of the following is not true during thermal equilibrium? Okay? Ang definition ng thermal equilibrium, there is no external excitation. Okay? Walang external excitation, walang voltage sources, walang light. There's no light that can release electron hole pairs. Nothing to transfer energy to the charge carriers. So true yon, no? There's no external stimulus. Okay? If there is generation, it will be equal to recombination. Okay? The Fermi level is constant, which is true for any electronic system that is under thermal equilibrium. Under thermal equilibrium, you only have one Fermi energy for the entire solid. And therefore, even by process of elimination, pwede na yung hulaan yung C, no? Although may choice na E. Oh, but yung zero current, actually, that's not true, no? Because you can have drift and you can have diffusion because of the internal forces inside your semiconductor. Okay? And then the degenerate semiconductor, ano ibig sabihin ng degenerate semiconductor? Ibig sabihin nun, it is super heavily doped. Super heavily doped. So pag super heavily doped yung semiconductor natin, it's already similar to, yung behavior niya is already similar to metals. No? The doping concentration is higher than 10 to the 18. Okay? And what happens is, because the dopants are already close to each other, they are no longer isolated from each other. They already interact with one another. They cannot be considered in isolation. Okay? Ito, I don't know where this statement came from. I guess binigay lang yan at random, no? But Pag tinignan nyo, parang, totoo kaya yan, no? Okay. Okay, which of the following statements is true about carrier action? Okay, all of these are false, obviously. No? The direction of drift is in the same direction as the electric field. Okay. And in diffusion is from higher concentration to lower concentration. No? Drift and diffusion can coexist. In fact, that's what happens in an open circuited diode. Okay? And then you have band-to-band recombination generation that is prevalent in silicon. It's one of the carrier actions in silicon. So, sorry, no? Band-to-band recombination generation is not prevalent in silicon, no? Mali, no? It's not prevalent in silicon. So the answer there is E. Okay, number 11. No? This is not true. What flows when a diode is reverse biased? What do you call that current? Reverse saturation current. So that is obviously not true. Okay. And then it all requires a little bit of computation, but the computation is very simple. Okay. Your V in is between 9 volts and 12 volts. So worst case for this to lose regulation is if this is at the minimum voltage. Yun yung kung manganganib to, no, na ito baka mawala sa 6 volts, it is when this is going to be at its lowest value. No? So if this is 9 volts, you have to make sure that the drop across your 100 ohm resistor will not be more than 3 volts. No? Kasi kung ito 9 volts, ibig sabihin ito, hindi pwedeng mas malaki sa 3 volts para ito will stay at 6 volts. So 3 volts, no? Teka. There's something wrong here. Load current, yeah, that's right. It's load current. Well, the load current, yeah. Parang mali ito. I just picked this up from the answer key, no? I think this is wrong. I'll get back to you on this, no? Because if this is 9 volts, no, this is 6 volts, this should not exceed 3 volts. Okay, what current flowing through here will make this 3 volts? Okay, it will be 30 mA. Okay, so I's of L should be less than 30 mA. That is at that point, no? At that point, that 30 mA, this is floating. In other words, this is biased. Pag tinignan nyo yung Zener curve, okay, you take a look at the Zener curve. So that is something like this. It is biased at this point, no? At this point, I sub Z is equal to 0. That's why all of the load current will be passing through. All of the load current here will be passing through this resistor. No? I'll get back to you on this. I think this should be the right answer. Okay. So for items 13 to 15, use the constant voltage model analyzing the diode circuit. Okay. If VI is equal to minus 3 volts, ang magta-turn on would be this diode. Okay. So D1 is on, D2 will be off. Okay. Now, what are the conditions for this diode to turn on? If you take the diode out, diba? Pag tinanggal natin yung diode, the voltage from your anode to your cathode should be greater than 0.7. That is the condition. So if VI is minus 3, ibig sabihin yung bottom is plus, yung top is negative. Okay, pag tinanggal ko tong diode na to, okay, this point will be at plus 3 volts. This point will be at 1 volt. If you consider this to be your reference, so the voltage across your diode is greater than 0.7. That's why D1 is on and D2 is off. Okay. On the other hand, if V1 is minus 0.5, okay, and D1, both D1 and D2 will be off. Tama, no? Minus 0.5, because if you take the open circuit voltage, if you take the diode out, you take the voltage across this, or you take the voltage across this, it will not be big enough for the diode to conduct. Okay? So both will be off. And if they're both off, ano magiging voltage? Open circuit yan, voltage divider, right? 10 ohms, 10 ohms. So kung ano man yung output mo will just be 1/2. 1/2 of your input. If VI is 2 volts, ito ngayon yung mag-on. Okay, this is what will turn on. If this turns on, this will be 0.7. So what is your output? Your output is 1 plus 0.7. So 1.7 lang. Okay. And then number 16, that's very obvious. Region or mode of operation, do we commonly set BJs for amplification purposes? Forward active. No? Forward active. We have to bias the BJT at the forward active mode so that it can amplify. Okay, 17. Which number pertains to electrons supplied by the base contact for recombination with the? So ito yung base. No? Obviously, this is your base. Okay. What are these? This is a PNP. If it's a PNP, that means from the emitter, you have holes that are traveling toward the collector. And a small percentage of that, okay, will go toward the base terminal and recombine with electrons provided at the base terminal. So obviously, ito yung sagot, no? Yung number 4. Okay, which number pertains to the thermally generated electrons and holes making up the reverse saturation current of the collector junction? So if this junction, collector base, is reverse biased, okay, what will be your current flow? No, your current flow will be reverse biased, no? So this is NP, reverse biased. So your current will be flowing from N to P, right? Kasi reverse bias. So these are thermally generated minority carriers. So obviously ito, number 3. Okay. And then number 19, which figure shows a forward active BJT? Emitter, base, collector, forward active. Pag forward active, ibig sabihin yung base emitter forward biased, yung collector base reverse biased. Pag forward bias, ano nangyayari sa built-in potential? Lumiliit. Pag reverse bias, yung built-in potential natin, lumalaki. So notice, from here, no, forward bias itong dalawa, so that yung built-in potential natin dito, lumiit. Ito, reverse bias naman, yung built-in potential natin, lumaki. So obviously, it's letter B. And then we know it is PNP, okay, because the built-in potential, it has the P side positive with respect to the N side. If it's NPN, the built-in potential the N will be negative with respect to the P side. No? So PNP siya. So yon, those are the answers to part 1. Any item there that needs further clarification? Yes. Number 6. Okay. Di ko pala nasabi to, no? A semiconductor material that is doped. So what does doping do? Doping increases the conductivity. When you add dopants, it increases the conductivity or decreases the resistance. Okay. So if you have a semiconductor material that is doped, it will have a resistance. It will. Okay, what does doping do? It decreases the resistance. Now, since the N-type, yung mobility ng electrons, ano mas mataas, yung mobility ng electrons or mobility ng holes? You remember? Electrons, right? Okay, so if you dope an N-type and a P-type equally, which one will have more mobile carriers? The N-type. And therefore, the conductivity of the N-type will be higher, or the resistivity of the N-type will be lower. That's why this is true. And then this is what I just said, no? When you increase the doping, your resistivity decreases. So these two are true. Okay. Any other questions? Any other questions? Number. Which of the following statements is true about carrier action? Hmm. Actually, they can. I'll get back to you on this. Huh? Like I said, I just picked up this answer sa answer to you. Yeah. Baka nagkamali dito. I'll bring up those two problems dun sa checker. Huh? Any other questions? Anyway, thank you for that. Any other questions? Okay. How many found this problem hard? Honestly. Saan ka nahirapan, if I may ask? Okay. Yeah. Medyo this might have confused you, and that's why we told you during the exam. Okay, if you're confused by that, just consider the capacitors to be open circuit and consider the inductance to be a short circuit. Because in DC, no, dito, you're being asked to solve for DC values. In fact, you're being asked in one and two, you're being asked to solve for the bias values. No? These are actually the quiescent currents. No? These are all quiescent currents. That is the value of your currents, no, at DC. At DC, your capacitor is an open circuit because X of C is 1 over omega C. If omega is equal to 0, then X of C is equal to infinity. X of C, you remember that from 1, 2, 3? That's your reactance. So it's infinity, so it's an open circuit. And then at DC, what is the reactance of your inductance? It's omega L. The impedance is J omega L. The reactance is omega L. Omega is equal to 0, so X is equal to 0. So this is a short circuit. So if you take a look at the equivalent circuit at DC, This is a short, this is open, this is open. So you can just forget that and forget this and then replace this with a short circuit. And now that looks like all of the circuits that you were asked to solve in your problem solving, di ba? Di ba? Kamukha na yan yung mga problem solving problems ninyo, no? And then pinadali pa niya yung problem. Paano niya pinadali yung problem? He said that, assume that beta approaches infinity. Anong ibig sabihin nun pag beta approaches infinity? Ano? Yeah, IC is IE. If IC is IE, what is IB? IB is 0. Right? Kasi if beta approaches infinity, ibig sabihin, IC is equal to IE, and therefore IB will be equal to 0. Ito yung IB natin, no? Let me use a different color. This is IB. Right? If beta is equal to infinity, IB will be approximately equal to 0. Or you can think of it that way, no? What is IB? IB is equal to IC over beta. Right? So if beta is equal to infinity, ito magiging 0. Okay, kung 0 yan, then this one becomes what? Just a voltage divider. That this becomes just a voltage divider. So right away, you can already compute for V sub B. So V sub B will just be equal to VCC R2 over R1 plus R2. Okay? Alam mo na yung voltage dito. Okay. If I know the voltage here, what is this voltage? If I know V sub B, no? If I know the voltage at this point, what is the voltage at this point? That's right. No? That's right. So this is V sub B. This is V sub E. V sub E is just V sub B minus 0.7 volts kasi andito yan, ano? VBE on is 0.7 volts. How do I get now VC? Ito. How do I get this voltage? Yes? Okay, yeah, that's correct. How do I get IC? Tama ka? Hindi pa natin nasa-solve yung IC, di ba? Pero how do you solve for IC? Ano yan? Yeah, gamitin mo yung VE kasi yung IC nga is equal to IE eh. No? Alam ko na yung VE. Right? Alam ko na yung VE. So VE over RE will just give me IC. So if I know IC, I know the voltage drop now here, and I can easily get V sub C. So hindi ba mabilis lang? Doing that would have taken what? How many minutes? I'm just curious. So how many got at least this part, number 1? Okay, that's good. Great. Nag-assume ka ng for C1, beta. Ah. Well, if you assumed a value for beta, like 100 or whatever, or 50, oh. Oh, if you assume the value for beta, ang makukuha mong sagot, okay, the value that you're going to get for V sub B is going to be smaller than using this formula. Well, yeah, I guess so, no? Kasi sinabi na assume that beta is equal to infinity. So kung sinabing beta is equal to infinity, dapat IB is equal to 0. Now, the way you solved it, you assumed a value of beta, no? Kasi doon ka sanay siguro, ano? So you assume the value of beta. Kung malaki yung value ng beta na ginamit mo, lalabas yung mga sagot mo would be near. It will be close. No? For example, if you use beta equal to 200, or maybe even beta equal to 100, no? It will be close. Okay? But it's not going to be exact. So depende na lang yun sa sa checker, ano? How much? Ano? Well, ang assumption mo kasi kontra dun sa sinabi ng problem, eh, no? So yun ang problema. Okay? Yeah. Okay, anyway, pag alam mo na yung IC, IB, and IE, well, actually pala, yun yung first part, ano? Yung IC, IB, and IE, yung IB 0, IE is VE over RE, and then IC is equal to IE, so that's and then you can now compute for VC, VB, VE, and then VCE. No? I don't think we have to do that anymore, no? Nakuha naman yun, no? Di ba? Yung sequence. Okay? And then from items 1 and 2, what is the value of I sub S? Okay. Maybe this is the first time you'll encounter this type of question, but this is just plugging in sa formula. Right? Because what is I sub C? I sub C is equal to IS e to the VBE over V sub T minus 1, okay, 1 plus VCE over V sub A. Right? And lahat nito given, no? Alam ko yung VBE. It's given. No? Here, VBE is given. Right? What else? V sub T is given. VCE is computed here. Kinumputan niyo yung VCE. VA is given. 80 volts yung VA. So dapat plug in lang. IC, kinompute natin yung IC, by the way, no? IC is also computed from here. So from that, dapat masosolve na nyo for I sub S. And then dito sa number 5, calculate GM, R pi, and RO. Okay, the formula for GM, R pi, and RO were not given dun sa cheat sheet, ano? That might have been an oversight. Yung gumawa nung cheat sheet, siguro hindi niya napansin na may problem pala na may GM, R pi, and RO. But the formulas are actually quite simple, ano? What is GM? GM is ICQ over V sub T. No? R pi is beta over GM, and then RO is equal to VA over ICQ. Okay. Kung talagang yeah, if you really did not remember it, I'm sorry, no, that you forgot that the formulas were not provided. By the way, no, ano yung lalabas na RPI? RPI should come out equal to infinity because beta is equal to infinity. In other words, para siya naging MOS transistor. Hello. Thank you. Okay, so actually problem 4 should have been a bit straightforward, no? Although yun nga, no, tricky lang yung part na baka hindi nyo na-realize nga na yung beta equal to infinity means IB will be equal to 0. This one, actually, this is my problem. Yes, it depends on the checker, ano. If your previous values were wrong but you use the correct formula, dapat there's some credit for that, no? I just don't know to what extent credit will be given. It's dependent on the person that's going to check the problem. Yeah, that's one of the problems with multi-step questions, ano, na pag nagkamali ka sa umpisang-umpisa, parang nagiging mali na lahat, no? Like of the gentleman here, no, na mali na yung first part niya, sana tama yung procedure niya dun sa next. Siguro naman bibigyan niyo ng some credit, ano. Dito, no? So for the circuit shown, Q1 and Q2 are identical with K equal to 20 microamperes per volt squared, VTH equal to 0.5, VDD is equal to 5. Fill up the table below for the given values of V sub I. So actually, we've been doing this a long time already, you know. In fact, we did this a lot, even dito sa module 4, no, dun sa when I introduced the first part, no. Given VI, what is the value of VO? Problema lang, dito, instead of your usual resistor, kasi usually resistor dito sa taas, okay, we have a MOS transistor. So made the problem a little bit more interesting. Dinagyan ko ng MOS transistor. Okay. What will be the operating mode of Q1? What will be the operating mode of Q1? It will always be in saturation. Q1 always in saturation. Okay, bakit? Dahil you notice this is VGS. Let's call it VGS1. This is VDS1. They're equal. They're equal. Because your drain and your gate are shorted together, then the voltage across your drain and your source and the voltage across gate and source and drain and source will be equal. Because VDS1 will be equal to VGS1. Therefore, VDS1 will always be greater than VGS1 minus VTH. Kasi kung equal sila, ibig sabihin, one will always be greater than the other minus a certain value. So it is always in saturation. So dito pa lang, pwede mo na sagutin yung operating mode ng Q1, no? Saturated, saturated, at saturated. Okay? Okay, so pag VI equal to 0, ano value ng I2, ID2? VI equal to 0. What will be the value of ID2? 0. Bakit? Cut off. Pag VI equal to 0, ID2 is equal to 0. What is the value of VO? I think this is where a lot of people made the mistake. Ano yung magiging value ng VO? Does anybody know the right answer? That's right, 4.5 volts. Bakit, no? Kasi let's take a look at Q1, no? For Q1, okay, ID1 is equal to 1/2 K VGS1 minus VTH squared. And this is equal to 0 because ID1 is equal to ID2. That's equal to 0. If that's equal to 0, that means VGS1 must be equal to VTH. But this is equal to VDS1. VGS is equal to VDS. Therefore, V sub O will be VDD minus VDS1. So that's equal to 5 minus 0.5. That will give you 4.5 volts. Any questions? So that's the easiest of the three. Kaya nga 5 points lang yun, ano? By the way, no, you have to check. You have to check your assumption of the operating mode. This is obviously cut off, no? Cut off because VI is less than VTH. Okay. Any question with regard to this? Okay, ngayon, VI equal to 2.5 volts. Okay. So let's assume. What will I assume? I'll assume that Q2 is saturated para ma-compute ko for ID2. No? So assume Q2 is saturated. So what is ID2? ID2 is equal to 1/2 K. VI is VGS1, so this is 2.5 minus VTH, that's 0.5 squared. K is, what is K? K is 20. So this is actually 10 times 4, so this is 40 microamperes. 40 microamperes. Just want to make sure. Yeah, that's right, no? 40 microamperes. Okay, so I need to compute for V sub O. For me to do that, for me to compute for V sub O, I have to know what VDS1 is. I have to know what the voltage across my top transistor is. Okay, and I can do that by computing for VGS1 because VGS1 is equal to VDS1. No? So ID1 is 1/2 K. What is VGS? What is VGS1? Oh, pala, no? Di pala natin alam yun yung ano, no? VGS1, okay, minus 0.5 squared, no? And this should be equal to ID2, which is equal to 40 microamperes. So this is, yeah, lalabas, this is K is 20, so this is 10. VGS1 minus 0.5 squared is equal to 40. If I compute for VGS1, this is quadratic, I'm going to get two values. I'm going to get two values. VGS1 is equal to either 2.5 volts or minus 1.5 volt. Ito hindi pwede to. Hindi pwede to. Ibig sabihin if VGS1 is negative, ibig sabihin cut off yan. No? But we know it's in saturation. So this is impossible. This is impossible. No? Okay, so let's check this. Ito we have to check. Okay. So VGS1 is equal to VDS1. That is going to be equal to 2.5 volts. Sorry, yeah, no. Yeah, that's equal to 2.5 volts, and therefore V sub O is equal to VDD minus VDS1, which is also equal to 2.5 volts. No? Yung VDD natin, V sub O is just the V sub O is just VDD minus VDS1, which is also equal to 2.5 volts. Okay, but V sub O is VDS2. Right? So notice that VDS2 is equal to 2.5 volts. VGS2 minus VTH is equal to 2.5 volts minus 1 volt. So obviously, VDS2 is greater than VGS2 minus VTH. So tama, it is really saturated. No? Remember, you have to validate all the time. You validate. So it's really saturated. Okay? So pwede na natin sagutin to. This is 40 microamperes. And this is going to be 2.5 volts. And then they're both saturated. Any questions so far? Okay. Ang medyo kailangan ng computation will be the third, no? Hanggang dun sa second, it's still quite straightforward. Okay, pagdating dito sa third at VI is equal to 5 volts. Okay, again, no, we can compute for ID2. So we assume Q2 is saturated. We can compute for ID2. This is 1/2 K 5 minus 0.5 squared. Okay. K is equal to 20. And I'm going to get, I have it somewhere here. Malaking value, no? Relatively. This is 202.5 microamperes, which should be equal to ID1. So now, I have an assumed value for ID1. I compute again what VGS1 is going to be. So ID1 is 1/2 K VGS1 minus 0.5 squared, okay, which is equal to ID2. So this is 202.5 microamperes. If I compute, I'm going to get VGS1, again, two possibilities. One is equal to 5 volts, the other is negative 4 volts. And I know this is not possible because that will cut it off. And negative VGS will cut off my transistor. So ito lang yung i-consider ko, 5 volts. If VGS1 is equal to 5 volts, that means VDS1 is also equal to 5 volts, and V sub O will be equal to 0. Right? Kasi 5 volts na yung VGS dun sa taas ko, 0 na magiging output ko. Kung 0 yung output ko, then Q2 cannot be saturated. Right? Because V sub O, remember V sub O is VDS2. If my drain to source is 0, for sure, no, if my gate to source is positive, for sure, my drain to source will be smaller than VGS minus VTH. So Q2 must be linear. Okay? So masasagutan natin dito, no? That this is going to be linear. Okay, ibig sabihin hindi tama itong value, no? Itong value ng current hindi tama. So if Q2 is linear, what happens, no? My ID2 is now going to be instead of the saturation equation, it's going to be K, okay, VGS2 minus VTH minus 0.5 VDS2 times VDS2. But this is remember, this is V sub I. Okay, so this is one equation. And then my other equation is this. No? ID1 is equal to 1/2 K VGS1 minus 0.5 squared. Because your Q1 is saturated. Okay. I have 3 unknowns, ID1, ID2, and VDS, and VDS, teka, ano ba yung mga unknown ko? Sorry. I equate these two, no? I equate these two. ID1 is equal to ID2, right? So I will have 2 unknowns. My 2 unknowns will be VGS1 and VDS2, right? But remember, VGS1 is also VDS1 because VGS is equal to VDS dun sa transistor 1. So I have 2 unknowns, VDS1 and VDS2. What's my other equation that I can form? What's the other equation I can form? Ito yung VDS2. Di ba obvious? Yeah. So ano yung equation na yun? The other equation is VDS1 plus VDS2 is equal to VDD. Right? So VDS1 plus VDS2 is equal to VDD, is equal to 5. Okay? So yun lang, no? If you solve for that, okay, and I'll just give you the answer, you're going to get VDS2 is equal to 1.32 volts, which is equal to V sub O. Okay? And then you can compute for ID2, and that's going to be 101.25 microamperes. Once you know VDS2, you can plug it into this to compute for ID1, which is equal to ID2. So that's your exam. Okay. So yeah, we still have a little bit of time, no? We just para hindi na tayo magkita on Thursday, let me just breeze through what we covered before. Before going there, any questions? May tanong? As swerte ka eh, if you do that, ano? Kasi, syempre, if you assume it's linear, and then you validate it later, and then you show that it's linear, then that's okay. So, walang problema basta validate mo yung assumption mo. In fact, usually dapat, I mean, before making an assumption, the correct thing to do is already try to guess what is the most likely operating mode, no? Kasi kung tama yung hula mo, you take less time to solve the problem. Kasi kung mali yung hula mo, you would have to solve it all over again, di ba? Using different set of equations. So usually, before you make an assumption, you try to guess ano ba talaga yung operating mode nito. Kung wala kang idea, then we always assume it's linear kasi mas madali to solve for your current if it is. Kung wala kang idea, we assume it is saturated kasi mas madali yung equation pag saturated. Mas mahirap pag linear. Okay. This is what I wanted to. Yeah. Sige, let's just go through this again, no? I already lectured most of this, but what I actually did was I revised the slides a little bit para kasi yun yung published in official material. So these are slightly revised. Okay, I'm not going to go through the parts which I think you should already be quite familiar with, ano? So, this is wrong. Dito, sorry. Let me, tapos na natin yung small signal model, no? Where were we? This is what I wanted to do, yeah. Wala, no? Okay, so already went through most of this, ano? Okay, so this is what should have been covered. An overview of the NMOS amplifier configurations, how to create your voltage transfer characteristics. I'll discuss the VTC of the NMOS common source. Kasi what we ended up doing dun sa first lecture ko was we discussed the PMOS common source, no? But actually mas usual na i-discuss muna yung NMOS common source. To determine the gain of that, the effect of the Q point on the output swing and gain. And then we'll go to the VTC and gain of the PMOS common source, the NMOS common gate, the NMOS common drain, and then just summarize everything. No? So these are the three topologies: the common source, the common gate, and the common gain. I already explained before that it's a little bit confusing. Pag sinabing, for example, common dito, no? Pag sinabing common source, paano ito naging common source, no? Dito naman, pag sinabing common drain, paano ito naging common drain, no? I already explained that to you, no? It's because it's with respect to the time varying component or the AC signal. Okay. And then we construct the voltage transfer characteristics using the large signal model, right? Which are the computations we've been doing for so long now, no? Yung large signal model. And what we do is we just do a point-by-point calculation. So may pagka brute force ng konti, no? So these are the equations that we use to consider both linear operation and saturated operation. So you have different expressions for PMOS and for NMOS, ano? And you have to be able to recognize when the transistor is in linear or in saturation mode. And so I said, okay, let's consider the NMOS common source. So titignan natin ngayon. So we we just fill up this table, we do the computations. I'm not going to go to the computations. Okay. But you have to take note of certain points of interest. One is the transition from cutoff to saturation. And that occurs when your input is at your threshold voltage. At that point, your current is still zero because VGS minus VTH is zero. So it's still zero. Pero andun na siya, no? Konting dagdag na lang ng VGS, magkakaroon ka na ng I sub D. And then the other point of interest is the transition from saturation to linear. And that occurs when VDS, no, is equal to VDS sat, which is VGS minus VTH. No? And so there, well, this is published already in UGLE, so there are computations which you can do. So I show the transition points here and here. So this is the transition from cutoff to saturation, and this is the transition from saturation to linear. And we add more points, and we get this curve. So usually, ito yung unang-una nakikita yung voltage transfer characteristic curve in a study of this subject matter. Where the points of interest are your transition from cutoff to saturation, that's point A. The transition from saturation to linear, which is point B. And when your transistor is deep into the linear region, which is point C. So when we operate the transistor, we normally, as an amplifier, we normally operate it in this region between A and B. And we look for a part where the gain is relatively constant. We try to look for a portion dito sa part na to where the gain is relatively constant. Because if your gain is changing, then you get some distortion. You could have operated it here, except that your gain is going to be very small. Dito naman, if you operate it here, your gain is zero. How do you compute for gain? You can write out the equations for the common source amplifier when operating in the saturation region. Okay. So, okay, this is your equation for your output. Output is, ito no, output is VDD minus IDRD. This is your output, VDD minus IDRD. And then we just substitute for ID this expression. 1/2 K VI minus VTH squared. And then we get the partial derivative of, or the derivative of VO with respect to V sub I. Because that is what we define as gain, the derivative of V sub O versus V of I. We get this expression, and simplifying, this is now our expression for gain. We can do that in saturation. It is difficult to do that in linear. Mahirap gawin yun sa linear because in linear, if you write out the equation for linear, it's very hard to isolate. It's very hard to write out an expression. In fact, it is impossible to write out an expression for V sub O in terms of V sub I. Hindi mo ma-isolate yung V sub O. So in the linear region, the only thing you can do is make an approximation based on delta V sub O over delta V sub I. And from the table that we earlier constructed, okay, this is going to be my gain. So dito sa saturation, I just used the formula directly, this formula. And then sa linear, I just made an approximation. Kaya walang laman to, no? Because I don't have any reference anymore for the next value of V sub O to be able to get V sub O minus to be able to get delta V sub O. So these are all approximations. This one are all using the formula. No? So again, plotting that, this is how your gain looks like. Okay, and then your points are marked here. Transition to saturation, the transition to linear, and then deep in linear. So if I take a look at the voltage transfer characteristic curve, the VTC, okay, ito yung pinapakita sa textbook natin, sa reference natin. If you take a look at microelectronics, no, by Cedra and Smith, this is exactly what it will show. Which notice is what this looks like. So we just managed to validate na tama yung sinasabi ni Cedra and Smith, no? Na ito yung magiging itsura ng VTC curve natin for a common source amplifier. Okay? Where he also shows the points of interest, that is A, B, and C. And if you relate that to the load line, so these are now your characteristic curves. Your output characteristic is your I sub D versus VDS. These are your output characteristic curves where VGS is a parameter. So these are for various values of VGS. So this is the load line. And you can identify A will be here, cut off. B will be here, no? where you have a point where VDS is VGS minus VTH. You're talking about this value of VGS. Okay, VDS is VGS minus VTH. So this is your transition from saturation to linear, and then this is now deep in your linear space. So that's A, B, and C. And your Q point will be somewhere between A and B. So this is my Q point. So if I'm going to choose a Q point, it will be somewhere between A and B. Okay. But usually I will confine it to somewhere in this region because here in this region, my gain is not constant. I want to look for a region where my gain will be more or less constant. So your Q point will have an effect on the output swing. So this is my VTC or voltage transfer characteristic curve. If I put my Q point too high, if my Q point is too high, and I apply now this input voltage, this is VI with respect to time. Okay. Pag paakyat yung VI, okay lang, ano? Ito, bababa to this point. And it is going to be more or less linear, no? Maybe there is going to be some nonlinearity here. Because remember what I said, no? You want your gain to be approximately constant, no? So obviously here your gain is not constant. If your gain is constant here, this will actually be a straight line. So you're going to get maybe some nonlinearity here. But here you're going to get severe nonlinearity. And then your signal is going to be clipped at BDD. So notice that okay lang yung positive excursion ng signal, pero pagdating dito sa negative, ang output ko magiging pandak na, no? Parang it was pressed downward. Obviously, this is a good reproduction of the input. On the other hand, if I choose a Q point that is too close to B, yung positive ko naman na ma-affect. Because as my input signal increases here, okay, my operating point will shift from here and will even go beyond B to the linear region. So it is no longer going to be operating in saturation. It will already enter the linear region here. And I'm going to get now this distortion. That distortion, no? Yung pababa, medyo okay pa. No? Dito, yung pababa, that's going to make my Q point travel from this point all the way up there. And maybe more or less that will be linear, but the bottom will be distorted. Notice that the gain is higher at this Q point than at this Q point, which is obvious because the slope here is smaller than the slope somewhere here. That's why malaki yung gain ko rito as opposed to that. And so you have a good idea where you should put your Q point. No, you put your Q point where you're going to get minimal or no distortion at all. No? So you try to choose a Q point where this line is more or less straight. Maybe this signal is a little bit too large. Because if this signal is too large, you're already starting to creep into the nonlinear portion. So maybe for this amplifier to be a better amplifier, we should limit the input signal to a smaller value para talagang diretso yung line natin dito. But anyway, I just wanted to illustrate that if you choose your Q point here, you have a better output. You have a nicer looking output. And then the choice of your Q point will have an effect on the gain. So this is the plot of the gain that we created earlier. So notice that at your Q point here, at V1, you have a smaller gain, a smaller absolute value of gain, smaller magnitude of gain. At V2, you have a larger magnitude of gain. And it appears that at the transition point, that is when your gain is maximum. But of course, you cannot put your Q point here. No? Hindi mo pwedeng ilagay yung Q point mo dyan because you're already going to get distortion. Your signal is already going to get pushed into the linear region. Okay, and then this is what we discussed, no? Ito yung diniscuss natin, yung common source. So I'm not going to breeze through this anymore, but this is the curve that we got. The only thing that I want to point out is the common source and the common source na PMOS and the common source na NMOS, the VTC curve is approximately the same shape, except that it's shifted to the right. And if you take a look at the NMOS, nag-uumpisa siya cut off, tapos saturation, tapos linear. You take a look at the PMOS, it starts in the linear region. So it starts in the linear region, and then saturation, and then cut off. Otherwise, the shape is quite similar. Okay, and your VO is this. So you have a different expression for your gain. This is going to be your expression for the gain. But the values of your gain are going to be comparable to the NMOS common source. So this is how your gain will look like. And then you can do the same thing for your common gate. This is what your VTC will look like for the common gate. Again, we avoid operating in this region. We don't want to operate where our output voltage is negative. So if we're going to use a common gate amplifier, we would want to bias it somewhere here, and then operate within the space that your voltage is always positive. You don't want to go down here. And you can compute again for your gain in saturation. And this is what your gain will look like. So for your common gate, your gain is now positive. Not like for your common source, where your gain is negative. Now the value of your gain is comparable. The common gate and the common source, the value of your gain is comparable. And then for the common drain, again, doing the same thing. Okay. This is your VTC. Okay. How do I compute for the gain? Okay, if you take a look at the equations of your common drain, again, you're going to run into that problem. It's going to be hard to isolate V sub O, make it in terms of V sub I, so that you can get the derivative of V sub O with respect to V sub I. Medyo mahihirapan tayo noon, ano? But one way you can compute for the gain is just trying to look for an area here, which is a straight line, and then getting the slope of that line. That will be your gain. And I did that from your inputs from 3 volts to 11 volts. And this is what comes out. So your gain is approximately constant from here to here. It is going to be a value close to 1, but less than 1. So if you remember the BJT, your common collector, no, or your emitter follower, ito yung katumbas ng emitter follower, no? Sometimes you call this your source follower. Your common drain or your source follower. It's usually used as a buffer. And in the BJT, your gain is very close to 1. Here, it's not as close to 1, but it's close. It's enough to 1. So this is usually used as a buffer. Okay, so that is supposed to have introduced you to how to create the voltage transfer curves for the various NMOS amplifier configurations from the large signal model of the NMOS transistor. You should be able to determine the gain in the saturation region of the various NMOS amplifier configurations. And you should now have a guide as to where to put your operating point. That's based on the criteria which you are supposed to follow. No? That criteria may be what is the maximum swing or what is the gain that you want. No? Usually yung dalawang criteria, swing or gain. Okay, this is published in UVLE. I have some exercises here that I want you to try on your own. We don't have time to go through that anymore. If you solve this, no, so I have 2 exercises, no, 1 and 2. If you solve this, you send me your solution. I can tell you if it is correct or wrong. I'm not going to publish the solutions. What I want to do is I want you to try it on your own, no? Because when I publish, or when we handlers publish solutions, the tendency of the student, they don't try to solve it anymore. They just try to study the solution. No? So what we want to do is we want you to actually try solving it, because it's only when you try and make mistakes that you somehow it's assimilated into you. So please try to solve exercise 1, exercise 2, and that will end module 4 for us. No, so I think we don't have to meet anymore on Thursday. So that will give you more time to work on your quizzes, and hopefully you can get started also on your problem set. Any questions? Any questions? Yes? How do you you want to max out the swing? So yeah, parang rule of thumb yun, ano? If you want to max out the swing and your input signal is symmetric, in other words, parang you're allowing your input signal, you're allowing the same amplitude sa positive as sa negative, ano? that's what you mean by a symmetric input signal, then usually you would try to look for a point that is halfway between uh, your maximum voltage and your cutoff voltage. No? Rather, your maximum voltage, well, depends on what configuration, ano? If it's an NMOS, it's your cutoff voltage, which is the maximum voltage, and your linear voltage. That's what you will try to do. But there's no hard and fast rule, ano? Kasi like I said, pag minsan yung curve mo hindi masyadong maganda, maliit lang yung region na parang diretso yung slope eh. So you also have to take a look at things like that. Any other questions? Okay, actually, you're going to find out later on, usually when we bias based on the common source. No? And then it's where you apply your input signal that will determine what type of configuration it is. Maybe I should explain that further. No, yeah, that's something that I probably should have. Just give me a minute. No? Okay. For example, no. Usually when you bias, this is already mga practical biasing circuits. No? If I have a MOS transistor, okay. So I will bias it in the common source configuration. So I will choose the proper values of R1, R2, and then RD and RS. I choose that. If I input signal here, and I get my output here, so this is V, this is VO, source, common source yan. If I apply my input signal here, and I get my output here, V capital O, yan common drain. My biasing was based on the common source, but my input and output makes this a common drain. Ano magiging common gate? Okay. Ang common gate ko, okay, so first I bias it based on the common source configuration. Dito ko ngayon i-apply yung input ko, V sub I. Dito ko ngayon kukunin yung output ko, V sub O. Or we capacitively couple it if you want this to be small o. No? If it's capital O, walang capacitor. If it's small o, may capacitor. This is common gate. Okay, that's how we usually bias your transistors. Okay, so anyway, yeah, that's all for today. No. Okay, so. We'll meet again Tuesday next week. Thank you.